Discovery of proton, the positive rays, since atoms are known to be electrically neutral and the mass of even the lightest atom, that is hydrogen atom, is about 1837 that of electron, it is obvious that an equal magnitude of positive electricity must also be present in an atom. E. Goldstein in 1886 showed the presence of another type of radiation that passes through the holes in the cathode and carries positive charge. These rays are called positive rays or anode rays or canal rays. Now, properties of positive anode or canal rays. These rays possess positively charged particles which are deflected by electric and magnetic fields, but the direction of deflection is opposite to that of cathode rays, showing that these particles possess positive charge. For the same electric or magnetic field, the magnitude of deflection suffered by positive rays is much smaller than that for cathode rays. Hence, positive rays of particles are much heavier than the electron. Second, their charge and mass are found to depend on the nature of the gas in the discharge tube. They travel in a straight line. They can produce ionization in gases. These rays affect a photographic plate, produce fluorescence and penetrate thin aluminum foils. The velocities of all positive ray particles are not the same. The velocities of these rays range from 10 to the power 5 to 10 to the power 6 meter per second. These particles contain unit positive charge which are later known as protons. Hence, proton is also another universal constituent of all atoms. Now, let's talk about the Thomson's atomic model. After the discovery of electron, J.J. Thomson, a British physicist in 1897, proposed a model of an atom. As atoms are electrically neutral, they have same positive and negative charge. According to J.J. Thomson's, atoms are simply positively charged lumps of matter with electrons embedded in them like raisins in a fruit cake. Now, defects of Thomson's atomic model. Identity of positive charge in an atom was not explained. Thomson proposed that when electrons are distributed, they start to vibrate above their equilibrium position and thus emit radiation of characteristic frequencies, but he failed to explain that these frequencies form a series. Thomson model of the atom showed by Rutherford's scattering experiment to be incorrect. Now, Rutherford experiment on scattering of alpha particles or discovery of nucleus. Ernst Rutherford in 1911 bombarded a thin sheet of gold foil about 7 into 10 to the power minus 7 meter thickness with fast moving alpha particle He plus ion obtained from a radioactive source from polonium or radon. While passing through the gold foil, the alpha particles scattered through different angles. A zinc sulfide ZnS screen was placed on the other side of the gold foil. When an alpha particle strikes the screen, it produces a flash of light and was observed by microscope. And with this, he found following observation. First, most of the alpha particle passed through the gold foil with a small deviation. Second, there were a few alpha particles that were scattered through large angles. Third, experimental results showed that about 20,000 particles suffered by an angle of scattering greater than 90 degrees. Fourth, a few of the alpha particles were even scattered directly in the backward direction, that is, angle of scattering equal to 180 degrees. Fifth, size of the atom is in the order of 10 to the power minus 10 meter, and the size of the nucleus is in the order of 10 to the power minus 15 meter. Sixth, the number of alpha particles scattered through an angle of theta is directly proportional to cosec to the power 4 theta by 2.